next point, which is, so yes, SVMs are a form of instance-based learning, but here's an interesting thing. The way they are usually presented in the literature is as a generalization of the perceptron. Remember when I said, the perceptron is very crude, right? It has all these limitations, and now we're going to put it aside, and we're going to do gradient descent, and multi-layer perceptrons and magprop are all going to be based on gradient descent, but the perceptrons, despite their perceived naivete, can actually be extended to something much more powerful. This is it, support vector machines. It's actually kind of a delicious irony, right, that, the dumb old perceptron that got so panned by Minsky and Papert, has come back, 30 years later as like the latest, greatest, most sophisticated, most powerful machine learning technique. I mean, support vector machines, as we'll see, are really perceptrons with a few, specifically 3 crucial things added, each of which kind of really magnifies the power. And in a way, what we're going to see here is those 3 things. And I can tell you up front what they are, and then one of them is this idea of kernels, which is the first one that we're going to look at. The other one is the idea of maximizing the margin, which is a different kind of objective function. And the third one is this idea of select variables to allow for noise. Okay, so these are the 3 things that we're going to see. Okay, but for the moment, right, here's the puzzle for us. So we've just saw, right, that support vector machines are kind of instance-based learning, right? And I also just claimed that they're really, a glorified perceptron. So how come, right? If you think about it, perceptron and, say, nearest neighbor, these are very, very different things, right? But somehow they must be kind of the same thing. Otherwise, the SVMs couldn't be both, right? So here's my question to you. What do you think is the relation between perceptrons and IBL? And really, this is the seed from which our whole understanding of SVMs is going to grow, right? Think about it. Nearest neighbor, on the one hand, is very powerful, right? You can form arbitrarily complicated frontiers provided you have enough data, right? They're going to all be like little chunks of hyperplane, right? Remember the Voronoi cells, right? There's these straight lines that separate, the region where one instance is from another. And perceptrons, is just, a single hyperplane. So how could they be, what could the relation between them be? You were raising your hand?
No.
Oh. Man, bummer.
They both have a linear or surface where they divide.
Yeah, sure. This is true, but this is you could say the same with decision trees, right? Decision trees is also linear surface, right? So actually, let me slightly refine the question and put it this way. I claim that the perceptron is a special case of instance-based learning. And this makes sense, right? Because in instance-based learning, you have, many different, pieces of hyperplane, and in a perceptron, you just have one, right? But concretely, right, how is perceptron a special case of instance-based learning?
Similarity coefficient is 1, I guess, for all the inputs. Then you could have weights for each input. So
not quite, at least at first sight, right? Because remember, in the perceptron, you're actually getting to the heart of the matter, but notice, in the perceptron, the weights are on the features. Right? If I have a data set with n instances and d features, in the perceptron there are d plus 1 weights. Right? Whereas in distance weighted nearest neighbor, the weights were on the examples. Right? In fact, there's going to be a very interesting relationship between these 2 in SVMs, but we're not there yet. Right? So, so hold that thought, right? So that doesn't seem to quite be the answer, right? So let me give you, anybody want to try something? This is a hard question, right? It's actually not obvious at first sight. So, anybody care to suggest something? Okay, so let me give one more hint, right? Well, let's just think of k nearest neighbor, right? Or even weighted k nearest neighbor. We don't have that many free dimensions to play with, right? But there's a very big one that we haven't touched on yet, and this is the similarity function, right? If you use Euclidean distance as the similarity function, right, you do get these Voronoi cells and this potentially very complicated behavior at no cost to you, right? But Euclidean distance isn't the only similarity measure that you could use, right? So here's my question to you. Can you think of a similarity measure such that k nearest neighbor with that similarity measure becomes the perceptron? in some sense, it has to be like a bad similarity measurement because it destroys the whole power of nearest neighbor, right? So what might it be, right? What could the similarity measure be that basically turns, all the part of nearest neighbor into just forming a linear frontier?
Kind of weighted.
Yeah.
Weighted mean.
Yeah, kind of. Right, so let's be more specific, right? So what I'm looking for is a way to compare two examples, right? So what are some ways of comparing examples that we've seen? There's Euclidean distance, there's Manhattan distance, right? Like there's L something norms, right? Yet there's another way of comparing instances, right? Which is actually used a lot, for example, in say information retrieval, right? And in a lot of areas for different things, which is the dot product. Right? Our good old friend, the dot product. Right? I just multiply the coordinates, one at a time, right? And I add all of that up, right? But in the perceptron, the dot product, right? Everybody remembers the dot product, right? In the perceptron, the dot product was being done between the weight vector and the example, right? This is what a perceptron is, right? It's just the dot product between the weight vector and the example, right? And then with threshold depth, right? This was the perceptron. But if we use dot product as a similarity measure in k-nearest neighbor, the dot product is happening between two examples, right? That's the difference. But number one, dot product is actually a totally reasonable similarity measure to use, right? Right? The more these things align, the more similar they are, right? Again, people use these things for information retrieval and whatnot, right? Also known as the cosine similarity, right? Because the dot product, after you normalize it, is really just the cosine of the angle, right? So the dot product is really, after normalization, is really saying, well, I will say that your examples are similar if you think of them as vectors. The angle between the vectors is small, right? This makes a lot of sense, right? However, using dot product as the similarity measure in nearest neighbor is a terrible idea because it makes the power of nearest neighbor go away. Right, because, as we just claimed, right, once you use dot product as the similarity measure, you've lost the ability to form very complicated frontiers. It all just becomes one simple linear frontier. So let's see how that happens, okay? So we're going to do nearest neighbor, right, with dot product as the similarity measure. Okay, so how? Actually, let's go at this from the other end. Let's start from the perceptron, right? And then see how this can come about, right? So my claim is the perceptron is just k-nearest neighbor with dot product as the similarity measure, right? So that's the claim. Now let's see why that claim is true. Well, first of all, here's my definition of perceptron. Okay? My class of my query example is the sign of the sum over all features of the weight of the feature times the value of that feature in the example, right? Everybody remember? This is the definition of the perceptron. I do the dot product of the weight vector and the feature vector. I put that through a hard threshold. If it's above 0, I predict 1. If it's below 0, I predict -1, right? So this is what this formula is saying. Okay? Now notice the similarities and the differences between this and what we had back here, right? Right? Here's my f, here's my sine of a sum of something, but now the something is different, right? So, we're partway there. And, the support vector, we saw that, this is IBL, right? So if we reduce things to that form, we're good, right? But here's the key observation, right? This is the key observation. This is really going to be important for support vector machines. What are these weights? Where did they come from, right? That's the thing, right? Something is happening inside these weights. And it's by figuring that out that we're going to arrive at the instance-based form, right? The key thing to realize is that, remember the perceptron training algorithm? The perceptron training algorithm worked as follows. If I classify this example correctly, what do? Right? I present the examples to the perceptron one at a time, right? And then I check whether the predicted class is the same as the real class. And if they're the same, what do? One word answer. Nothing, right? I do nothing, right? It's error-driven learning. If you're getting your examples right, go home happy, right? Don't go fixing what I broke is, what's behind that type of learning, right? What happens, however, when you get the example wrong? When the example is wrong, some weights change, right? In particular, the weights of the features that agreed with the class go what? Up or down? Those go up, right? And the features that disagree with the class, those go down, right? Because I want to make this thing be above threshold when it was below before, or vice versa, right? So if you think of this as what's happening to the weight vector, right? I have a weight vector, right? And now along comes a new example. Let's suppose that I get it wrong, right? And what this causes is some change to the weights, right? But what is that change to the weights? If you think about it, that change to the weights basically consists of adding the new example to the weights with a weight that's going to be the learning rate. Remember the learning rate, right? If the learning rate is 1, actually I'm just adding the example, right? But each feature is going to be added with a sign that depends on whether it agrees or disagrees with the class. Okay? So this is the key realization, is that the weight vector at the end of the day is just a weighted sum of examples that you've seen. The weights are going to depend on the learning rate and are going to depend on the classes, but here is in a very short expression what's really going to happen at the end of the day. Is that my weight of feature j is going to be the sum over all my examples of alpha I, which could be 0 if the example was not used, right, of the value of the feature times the value of the class, right? Because all that's going to happen at each stage is that you're going to add this, right, to the weight of the feature, right? If you don't add it, the alpha I is 0, right? If you add it, you get a contribution of eta, the learning rate, right? So this alpha, right, is just going to be eta times the number of times that I had to make corrections, i.e. the number of mistakes that I made, as my perceptron was learning. Okay, did everybody get this? Right. So this weight, right, this innocent-looking thing here, is really at the end of the day, right, the weight vector is just a weighted sum of examples. Okay. Any questions about this? Okay, so if you believe this and you believe this, then let's combine the two. Let's replace wj in here by this expression, right? So here it is, right? I now have the sign of the sum over the features of this thing, which used to be wj times xqj. Okay, so I just replaced one into the other. Okay, and now let's try to simplify this. Let us, switch the ordering of my summations, which I can always do, right? Because addition is commutative, right? So I can push this sum over j inside the sum over I, and in fact I can push it past the alpha I and past the yi. Why is that? I can push this summation all the way to here, right? Why can I push the summation over j past alpha I and yi?
Because they're constants over j.
Exactly. Alpha I and yi do not depend on j, right? So they can be put outside any sum over j. But then here, now I hit xij and xqj, and that definitely depends on j. Okay. So what do I get? I get sum over I of alpha I yi, sum over j of xij xqj. And what is the sum over j of xij xqj? It's just the dot product of of xq and xi. Right? You agree? Right? Sum over j of xij xqj is just the dot product of xq xi. Right? Remember, j is ranging over the coordinates. Okay? Everybody agree? So now look at this very interesting phenomenon. This formula now looks just like the formula that we laid out in the beginning for SVMs. Right? What is f of xq going to be? It's going to be the sign of the sum. And notice this is now a sum over the instances, not a sum over the features, right? This is what we wanted, because that's what happens in instance-based learning and therefore in support vector machines, of weights times classes. And now the only difference is that before, right, we had the kernel xq xi, right, the similarity between xq and xi. And now we're just using the dot product as the kernel, right? So, very contrary to appearances, the perceptron is really just a special case of instance-based learning. Okay? Questions about any of this? And this is going to have powerful consequences for support vector machines. In particular, so here's the idea, right? Perceptron. right, poor thing. It can only learn linear frontiers, right? Well, here comes the first big trick, known as the kernel trick, right? This is the technical term, is the kernel trick. The kernel trick is, I'm going to take my dot product, and I'm gonna squint at it and say like, oh, you, my friend, the dot product, you're really just a kind of similarity function. You're just a kernel. But now I can look at this expression and say like, well, why use only the dot product, right? Let me replace the dot product by any kernel, right? And suddenly my perceptron has become a very powerful thing. But all of the things that I knew about learning perceptrons in various ways will transfer over to this more powerful case. So in a way, the Perceptron's revenge, right? The reason it has come back, morphed into a super, algorithm, whereas before it was like this, little turtle crawling along on the ground, is that now I've embedded the kernel in there. And by embedding the kernel, I've gone to only being able to form linear frontiers to being able to form, very rich and complex frontiers. Okay? And, we will see all this play out shortly.